So today I am going to talk about a very important theorem, that is Poynting Theorem, and I will also discuss the definition of or the pictorial representation of Poynting vector in this lecture. So an English physicist named John Henry Poynting first pointed out that an electromagnetic wave can transfer energy from one point to another point. And Poynting theorem was given, and regarding this he has given the theorem known as Poynting theorem, and during the definition of this we will define a quantity. That quantity is known as Poynting vector. Right. So, and what this Poynting vector will represent? This Poynting vector will represent energy density or energy flow per second. Per unit area. So let us now use Maxwell's equations to derive Poynting theorem. Let us now use Maxwell's equations to derive Poynting theorem. So for this, consider two equations. One is del cross E is equal to minus curly B over curly T, and another equation which I am considering, that is del cross H is equal to curly D over curly T plus J. These are the two equations which I am considering. Now operating these twos with H means taking dot product with this, and here we will operate with E. So when I operate these two with these, then what will happen? This equation will become H dot del cross E is equal to minus H dot curly B by curly T, and here this equation will become E del cross H E curly D over curly T plus J. Right, these are the two equations which I am getting. let us call it as equation number 1 and this is equation number 2. Now let us apply the operation, that is 1 minus 2. So if I apply this operation, then what will happen? This is H dot del cross E minus E dot del cross H equal to minus H curly B over curly T minus E curly D over curly T plus J. So let us apply a very interesting identity. As we know that del dot A cross B is equal to B del cross A minus A del cross B. So if I try to look at this using here and if I apply this identity here, then what we are getting, this will become, this is del H cross E, del E cross H. E cross H, we can write it down in this way, and here these quantities will remain as it is, right? So it is minus H curly B over curly T minus E curly D over curly T plus J. So it can be written as H curly B over curly T minus E curly B over curly, not curly B, but it is curly T over curly T plus E, not E, but it will also become minus E J, right? That's what we are getting here. So let us take these two terms separately. So first of all, let us consider this, and then after this let us consider this, and let us simplify these two equations, and let us call this as equation number 3. So this H curly B y curly T, it can be written as H curly mu H over curly T, and here mu can be taken outside, so it is mu H curly H over curly T. And let us consider this part now. To try to understand this, let us recall that curly H square over curly T, it can be written as, because H vector square is simply can be written as H square, so that's why I can write it down as curly H square over curly T, and this can be written as, or this may simplifies to, first of all let us do one thing, this can be written as 2H vector curly H vector over curly T, but this can be written as curly H square by curly T square is equal to 2H vector curly H over curly T. But this 2, if I bring it towards this side, then 1 by 2 curly H square over curly T square can be written as H curly H over curly T, I bring this 2 towards this side, so that means this part will become 1 by 2 mu curly H square over curly T square. This can be written like this, right? And similarly, as we know that this D is equal to epsilon E, so if I use this here, then in the similar fashion this E curly d over curly t can also be written as 1 by 2 epsilon curly e square over curly t square. It can also be written in this way, right? And another thing which I will use, that if I will use these two things here, one is this and another one is this, for this, right? Then this equation number 3 will become, this equation number 3, it can be written as if I put these, then this del E cross H is equal to minus 1 by 2 curly over curly H. This mu can be taken here, so it can be mu H square minus 1 by 2. Similarly, this can also be written here inside it, so that means it can be written as 1 by 2 curly over curly t, sorry, I am mistaken little bit here, it is curly over curly t, right? So yeah, so it is curly over curly t epsilon e square and minus e dot j. That's what we are getting here. And let us make it more simple. Del E cross H is equal to 1 by 2 with negative sign and curly over curly t, and inside it is mu H square plus mu E, sorry, not mu, but it is epsilon E square minus E dot J Now taking volume integral on both sides, integral on both sides, sorry, not, there is no need to take volume integral, but let us do one thing. You can write it down as E cross H is equal to minus curly over curly t 1 by 2 mu H square minus epsilon E, sorry, plus epsilon E square minus E dot J. And if we bring this towards here, E cross H, and let us call this as equation number 4, it is equal to this one, and sorry, bringing this towards this side, then curly over curly t mu H square plus epsilon E square, it is 1 by 2 equal to minus E dot J. Right, so that's what we are getting here. Now let us try to understand and what does it mean. And here we recall this quantity as S vector, and this is known as Poynting vector. I will talk about it later in this lecture. This is known as Poynting vector. So it means del dot S plus curly over curly t, and let us call it as W, this quantity as W, is equal to minus E dot J, and let us see what these terms will represent. So here this is known as Poynting vector, and I will talk about it later. And what this term, this W will represents the total energy stored, and this E dot J, because it is a negative sign, this represents that E dot J, it represents the energy dissipated, right? So this equation number 5 is known as the Poynting theorem. This equation number 5 is known as Poynting theorem. And let us try to express this in the integral form. So to represent this in the integral form, let us reconsider equation number 4. This is the equation number 4. Let us write down this equation again. So if I write down this equation again, then I can write down this del dot E cross H, and E cross H is equal to minus 1 by 2 curly over curly T mu H square minus epsilon E plus epsilon E square minus E dot J, and let us take volume integral on both sides. So if I take volume integral, then it can be written as del E cross H, and E cross H we have defined it as S vector. So it is it can be written like this, and it is curly over curly T and 1 by 2 can be taken outside. So 1 by 2 mu H square plus epsilon E square, and let us take its volume integral. dV is equal to E dot J dV, its volume integral with negative sign. Also we know that using Ohm's law that J is equal to sigma E. So it is the Ohm's law in vector form. So if I use this here and I put it as S vector, as a Poynting vector, then this integral will become also, if I applied Gauss's divergence theorem, here, then it will become surface integral of S E cross H is equal to, not equal to, but plus curly over curly T 1 by 2 mu H square plus 1 by 2 epsilon E square, not 1 by 2, but it is epsilon. Better if I write down it in this way, right, equal to minus sigma E square dV, right? So let us put it as S, not E dot, but it is E cross H. So it can be written as surface integral of S ds is E plus curly over curly T oh, dv will also be there. It is 1 by 2 mu h square plus epsilon e square, and dv, its volume integral, equal to minus sigma e square dv, right? That's what we are getting. And this equation is known as integral form of Poynting theorem. Right, that's what we are getting here. And let us try to understand each term separately, what this term represents and what this term represents. So this term will represent the total energy stored within the enclosed surface, having volume V, and another term, that is this term. What this term will represent? This term will represent energy being dissipated, dissipated within the enclosed surface. Right? So this is the basic idea which we are getting from here. So let us now re-express this theorem in words. So let me rewrite down this equation again. So as I have derived that is equal to negative of volume integral of, if I bring this towards that side, I am just rewriting it as, sorry, not this way, what this is equal to negative curly over curly t, this volume integral, this is 1 by 2 mu h square minus epsilon, sorry, plus epsilon e square dv minus e square dv. These are the two terms, both are negative. So what this means, that as given in the Griffith, that Poynting theorem says that, according to Griffith, it was explained in Griffith that Poynting theorem says that work done on the charges, charges by electromagnetic force is equal to decrease in energy stored in the field and less the energy that flowed out through the surface. Right, so this work done on the charges is represented by this term, and this electromagnetic and decrease in energy stored is represented by this one, and less the energy that flowed through the surface, it is represented by this term. So this is the statement of Poynting theorem. So as I talked about in this lecture, Poynting theorem, and a new term will be encountered, we call that as the Poynting vector. So let us have a brief look at the Poynting vector, that or how we look at this Poynting vector diagrammatically or pictorially. So let me talk about now the pictorial representation of Poynting vector. Right, so if I recall electromagnetic wave equation, then del square E is equal to mu epsilon curly square E over curly T square, and for magnetic field I can write down the equation as del square B is equal to mu epsilon curly square B over curly T square, or this equation can also be written as del square H is equal to mu epsilon curly square H over curly T square. So let us now consider that wave is traveling along x-axis, wave is traveling along z-axis. Let us do one thing, let us draw a diagram. So what I am considering, that electric field is varying along x-axis. It was like this, electric field vector is varying along this direction. So electric field vector is varying along x direction like this, and if it is varying along, that means it is moving along x direction, it is z direction, say it is x-axis and it is y-axis. So it is the variation of electric field. And say this quantity is known, it means maximum amplitude of the electromagnetic wave is E0, and say this magnetic field is varying along this direction. It's like this, right? It is varying along this direction. And here this is H0 is the maximum variation. So that means this is Ex and this is Hy, it is along this direction, and wave is propagating along the z-axis. So that means the wave propagation is along Ex cross Hy, right? So in simple words, if I say that electric field is moving along the E and magnetic field is represented by H, then the wave is propagating along E cross H. Wave is propagating along E cross H, right? That's what we are getting, and we call this quantity as the Poynting vector. Right, and what does it mean, what this E cross H means? So let us have a look at that. What does it mean? Say it is E cross H is equal to, say, E is the voltage upon length, and this H is basically current upon length. So that means it is voltage into current upon length square. So what does it mean? It means that it is voltage into current represents electric power, and this is area, so it is watt per meter square is its unit. Now this power means what? Power means energy flow per second. Power represents energy per second. Energy per second. Therefore, E cross H will represent what? This E cross H will represent the energy flow per second per unit area. So here I talk about the physical significance, or what this Poynting vector will represent the here, and its pictorial representation. So this is all about this lecture, and I think this lecture is quite interesting, and the Poynting theorem and the Poynting vector, these are the very interesting concepts which are emerging out, right? So that's all for